Thanks. I'd like to thanks the organizers for inviting me this nice workshop. And in this talk, I'm going to talk about introduce my research work, collaborate with Mingi Han and Youngrong here, and which is about the state discrimination. So I think you are already familiar with this topic, but except the non-destructive part. So I will mainly explain why we consider this such an additional term and then what the advantages are from it. So let's begin with a short review of the conventional state discrimination. So here is set up. There are referee and receivers. So referee Charlie chooses a state from a set of state let's assume the pure state K pure state is indexed at Z, and from Z is from 1 to K, and with some probability distribution PG. And then after receiving the state, the receivers allow the measurement and operations. For example, LOCC is a very natural choice, and from the measurement outcomes, they can guess which states came, and so they decide the guess is G, and then send it back to Charlie. And finally, Charlie can check the guess is correct or not. And this is a conventional state discrimination setup, and the success probability can be written as this form, and PJ as I said, is kind of a state probability distribution within the state, and then P lambda condition on Z means that it's kind of a probability of a measurement outcome lambda for given state rho Z. And then this important part is cost function is delta function. So where this if it gives 1, if there is a certain function from the measurement outcome alpha lambda to the correct answer Z, otherwise it gives 0. And then there were no results where these for non-orthogonal case, we cannot perfectly distinguish those states with certainty because of no cloning theorem. And on the other hand, for orthogonal states, we can always perfectly distinguish them if there is no restriction on the power of allow operation in the receivers. But this is a trivial case. However, if we have a certain restriction, for example, LOCC, then this problem becomes highly non-trivial, which I will explain. So let's look at this entanglement in the state to be discriminated and local distinguishability. And then one might expect that if there is no entanglement in the state to be distinguished, then LOCC is enough to distinguish them with certainty. And on the other hand, if there is entanglement in the state, then we should use the non-local measurement, which means that LOCC plus additional mutuality entanglement as a resource. So it's a very naive but natural intuition. But the fact is that this is not the case, because first counterintuitive example is that there is an example of a set of product state which cannot be perfectly discriminated by only using LOCC, called the non-locality without entanglement. And the other extreme case is that for any two pure orthogonal states, we can always distinguish them with certainty by only using the LOCC. regardless of how entangled they are. So because of these counterintuitive examples, we cannot find a simple relation between the entanglement in the state and then local distinguishability. But still, we can ask the question, can you find the sharp boundary between local and non-local measurement? In other words, LOCC and beyond the LOCC by twisted such a conventional state discrimination test. And it's linked with the main motivation of our work, so called seeking boundary between classical and quantum. So it's a kind of, roughly speaking, it's there's a classical world, and then it's a subset of the quantum. And then let's think a procedure says, so first we set a task here, the state discrimination, and then we can define the classicality, here the LCC or local measurement. And then the next step is to find the limitation of the classicality. So in this case, the which corresponds to the maximum success probability of the discrimination test or some upper bound by achievable by LCC. And then if we need a more higher success probability, then we should use additional entanglement as a non-local measurement, a resource of non-local measurement. So in this case, we can claim this usefulness of entanglement as a resource in state discrimination test. So this is a very natural and main motivation, but more physical motivation is here. So it's from those fact that the person is measurement can disturb the state. And at the same time, we need measurement to gain information for discrimination. So if we think the parameter on disturbance and success probability of local discrimination, then we can expect that this kind of trade-off relation between those two information. And this is practically important because also practically important because let's look at this situation that we need to reuse the entanglement after the discrimination for the consecutive information processing. Then this trade-off relation helps to us to find the computer entanglement cost of the discrimination and reconstruct the entanglement. And so we can choose a proper strategy for depending on our purpose. So this is another motivation. Then, so we suggest non-destructive state discrimination as by adding another step to check the disturbance of the state. So here is our D is the blue dashed box is our additional setup. And so as I said, this is the success probability of the conventional state discrimination. And then it becomes other form for our task. So there is one additional cost function, in this case fidelity, and to check the disturbance of the state. And then which can be rewritten as in terms of the cross operator. And our main result is, first main result is on information trade-off in state discrimination. So this is our main theorem, and we consider the separable cross operator to cover the separable measurement. And so this we actually found upper bound on the success probability of our task, our non-destructive task. but then it depends on the local dimension and then and the Schmidt coefficient of the initial state. But the simpler version is if we consider the equally distributed maximally entangled state, which means it corresponds to PC is 1 of K and local dimension is same as V, then this success probability of our task is bounded by 1 of K, and then also equal to and the multiplying success probability of conventional discrimination task and fidelity here. So which has several physical meaning. It indicates the trade-off between the success probability, in other words, local distinguishability and fidelity. And the second one is that if we impose a non-destructive condition, which is F equal 1, then the power of LOCC is highly maximally suppressed as the it's the same as the random guessing because it's 1 of K, it's just random guessing. And compared to conventional state discrimination task, it's known that the upper bound is D over K. So our is just 1 over K. There's a huge gap between ours and conventional. And second window is let's look at this equation. We have in the first video we have seen that our bound is 1 of K with the local measurement or LOCC without entanglement, without the pre-shared entanglement. But we know that if we supply the unlimited of the shared entanglement, then we can reach the unit success probability in any case because the local measurement can be global measurement. But the problem is how much the entanglement we need. So our second result is that we found some one of the upper bound. So if the local parties share the C-EV entanglement, then this bound is 2 to the C over K. And the next question is how to achieve this bound and how tight. So we first consider a simple strategy is called teleportation and preparation. It's very simple, but it's very powerful in the conventional state discrimination test. So it's okay. Let's look at the very simplest example. So discrimination, non-destructive discrimination of bad state. And so the conventional state discrimination task, the entanglement cost to achieve unit success probabilities here. So if when the K is 2, then this cost is 0 because as I said, for any 2 states we can locally distinguish them. And K equal 3 and 4 case, and the entanglement cost is 1, obviously, because we just use teleportation by consuming the 1 EBIT to localize. Then we can just distinguish them with the local measurement. And this is known to be optimal. But in our test, we need to reconstruct the entanglement after the discrimination. So and our bound here means that K equal 2 and 4 cases, and then this bound is 1 or 2, but this can be simply achieved by the teleportation and reconstruction because just first we just use a conventional strategy and using teleportation and consume the additional 1 EBIT to reconstruct the bad state. So K2 and 4 cases as saturated our bound, but we don't know this is actually optimal bound. But for three cases is interesting because it does not saturate bound, and then we can think we can ask a better strategy for non-destructive discrimination test. So our answer is yes. So we use a stabilizer method and fully non-destructive way to in the strategy, and we know that bell states can be represented by the stabilizer generators and with plus minus sign. And then if we can perform the measurement of this form, then we measure the sign of the generators with a non-destructive way. But this should be the non-local measurement. So we need additional entanglement to construct such a non-local measurement. And this our strategy is summarized with this one picture, and it's kind of we use additional band state or EBIT and control the Pauli operator to measure to get the sign information of Pauli operators and for example, three band state is enough to show the strict gap between our strategy and conventional interpretation strategy. So there's any three bell states without loss generality can be chosen, then which is represented by this side table of the stabilizer generators. And then in each of these boxes, for each of these boxes, we need one EBIT. So in the table, if we first measure the sign of the Z generator, then if outcome is the sign is minus, then we can finish the whole strategy because we know that the state is by 2, and then if the outcome is plus, then we can do the same procedure once again for this excess generator, and the total average cost is 5/3 is strictly less than 2, which is the cost in the conventional teleportation and reconstruct method. Okay, so ours from the conventional one, and we can extend to these more general cases where the test protocol several pairs. So in this example, we consider 6 of 3 pairs, and I skipped it, but this cost of our strategy, non-destructive strategy, is 8/3. But we show that we prove that this teleportation and the preparation has a cost of 3 EVs. So there's a 1/3 EV gap. And this is interesting example because it has an implication to conventional discrimination in entanglement cost. There is overall entanglement cost point of view, and which means that let's think that after the discrimination, then we have one of 6 three pairs. They have 3 EV of entanglement. Then, which means that our entanglement cost for the non-destructive scheme is 8/3, and finally we get 3 EV entanglement. Then 1/3 EVs remain for each discrimination, which means that we have for the receiver's point of view, they have an entanglement only for discrimination, but this is not a free launch, but just the referee supply the entanglement. But anyway, in the referee's point of view, are on they are owning entanglement, additional entanglement. This is interesting because there were notion of the entanglement discrimination analysis in the national state discrimination task literature, and but if they use just destructive scheme, then the zero net entanglement is okay, but ours is outperforming. Outperforming does just zero entanglement cost, but ours is only that only. So I can say shortly about this application. So one of our application is entanglement certification. So as I mentioned that this bound is bound indicate the boundary between the local LOCC and beyond the LOCC. So which means that if we perform the non-destructive state discrimination and with the K maximum integral state, and then success probability of our test is bigger than 1/k, then there should be pre-shared entanglement between local parties. For example, entanglement at the quantum network. So which means that we can confirm the entanglement. It's a kind of entanglement certification, and our advantage is is non-destructive. So after certification, we can use reuse the entanglement to further quantum information process, and we can generalize to the tripartite case because our strategy using the stabilizer formalism and then to multipartite stabilizer and more generally real quantum network, and we can think absolute maximum state. And okay, to summarize, our contribution is set a clear boundary between LOCC and beyond LOCC operation in state discrimination task, and we found the trade-off between information trade-off between the local distinguishability and state undisturbance. And finally, we provide efficient adaptive strategy using reusing entanglement in our task. And this ongoing project is we are generalizing to mixed state and particular valence state to cover the noisy cases in a particular scenario. And there are often problems, so we didn't prove the optimality of our strategies. We just suggest a bound and some strategy, but we don't know optimality. And for non-stabilized state, we don't know. So this is transitive protection. For example, double state. Thanks for attention.
Much questions? Okay, if there are no questions, like what do you do to try to prove optimality? Did you like take some entanglement monotons and try to show that they are non-increasing under those while during your protocol, or?
Yes.
Like, could you violate monotonicity if you could get a better bound, for example?
For future work, I mean, what?
No, like to prove the optimality of your protocol, right?
Optimality.
Could you say if you like find a better
Yes, yes, yes. Okay, so we can think the kind of thermodynamic arguments to use how to what's the problem for the non-destructive cases. Also, we just give a non-destructive strategy, but for destructive strategy, we should destroy the entanglement and reinsert the entanglement. And then in that procedures, I think we might lose some uh, efficiency of entanglement. So we can use this to prove the optimality of it.
Okay, thanks. Any other questions? Well, if not, then thank the speaker and all the other speakers again.